Section: Introduction. In this section, we discuss the growing use of transformer neural networks in various technologies, despite our limited understanding of their inner workings. This lack of understanding raises concerns about their reliability, especially in critical situations. To tackle this issue, we draw from both bottom-up and top-down analyses, as well as research on modularity. Our goal is to investigate how different parts of neural networks specialize in specific tasks and access different knowledge bases. We define modularity as having two main characteristics: a clear separation of components with different functions and the close physical arrangement of these components. For our methods, we utilize a vision transformer, known as VIT-Base224, and a causal language model called Mistral 7B Instruct version 0.2, both accessed through the Hugging Face Transformer library. We analyze both the pre-trained models and a randomly initialized model. We focus on the neurons in the MLP layers, specifically those activated between the input and output weight matrices. In terms of datasets and tasks, we use VIT for image classification on the CIFAR 100 dataset, treating it as a baseline. For the forget datasets, we use superclasses from CIFAR 100. For the text models, we explore next token prediction and question answering across various text categories, using Eleuther's, the pile, for a broad baseline and additional specialized datasets for specific subjects like biology, physics, and chemistry, as well as GitHub code. For neuron selection, we apply a method similar to selective pruning. We score neurons based on the mean absolute deviations between a reference dataset and an unlearned dataset. We then select a subset of neurons relevant to a specific data subset by choosing those with the highest scores, aiming for a targeted drop in accuracy when these neurons are removed. We also implement mixture of experts clustering to group neurons into clusters. This involves treating the input weights of an MLP layer as vectors and applying balanced k-means clustering. This method helps us identify groups of neurons that activate together, facilitating expert selection during inference. We use 96 clusters for VIT and 128 for Mistral, comparing the structures of trained and randomly initialized models. Finally, we evaluate VID's performance across CIFAR 20 classes to see how deactivating neurons for one class impacts others. We find that classes with similarities often share neural pathways. For instance, neurons pruned for insects and non-insect invertebrates show significant overlap, and classes like fish and reptiles also exhibit correlated performance drops. Interestingly, the impact of unlearning one class on another is not symmetrical, although they are related. As we aim for an 80% drop in accuracy, we notice a decrease in selectivity, likely due to strong signals from the unmodified attention layers. Section Summary. In this section, we explore the modularity of transformer neural networks by analyzing the specialization of their components in performing distinct tasks, using vision transformer and Mistral models. We employ methods like neuron selection and mixture of experts clustering to assess how deactivating certain neurons affects performance across different classes, revealing shared neural pathways and asymmetric impacts on class performance. Section: Mistral performance. In this section, we investigate how a decrease in performance in one class affects performance across other tasks in the dataset for Mistral. We set a goal to selectively prune until we achieve a 20% drop in the accuracy of predicting the next token for each unlearned text subset. Our observations show that unlearning certain topics, like biology, leads to expected drops in related areas, such as high school biology, in MMLU. Notably, unlearning PubMed Central significantly impacts various medical subjects, while unlearning Archive also affects related MMLU topics. However, we find some exceptions, like Europarl and Free Law, which have minimal effects on related topics. Interestingly, in some cases, performance even improves, such as a 118% increase in abstract algebra after unlearning code. Unlearning fill papers has a notably negative effect on Europarl, more so than the reverse. These findings suggest that our selective pruning method effectively identifies general features of the model, though there is room for improvement with more advanced methods and datasets, hinting at a potential for interpretable modularity. Next, we analyze how selected neurons overlap between different classes or data subsets. For two sets of selected neurons, we calculate the ratio of overlapping neurons to the total in one class. We find that selected neurons represent about 12.5% of neurons in VIT and 3.4% in Mistral. Our results indicate that pre-trained neurons show distinct activations compared to randomly initialized models, with similar overlap patterns but varying magnitudes. We observe three main trends. More neurons have overlaps closer to the median, extreme overlaps decrease based on class dissimilarity, and similar classes gain larger overlaps. These trends are consistent in both pre-trained and randomly initialized Mistral models, with a notable correlation between overlaps in both types of models, suggesting evidence for the weak lottery ticket hypothesis. Finally, we measure how selected neurons cluster within layers, inspired by the Lorentz curve and Gini coefficient. We count selected neurons in each cluster, sort them, and plot a cumulative distribution. We normalize the area under the curve to assess distribution, where a value of 1.0 indicates all neurons in one bin, and 0.5 indicates an even distribution. Our findings show that pre-trained neurons align more closely with modification clusters, especially in earlier layers, while later layers exhibit a bimodal correspondence. This suggests that the clustering in layers near the input is more predictive of class than in central layers.